Hi everyone, my name is Mayank Jha. I'm a senior machine learning engineer at Amazon, where I work on large scale machine learning systems and intelligent robotics. My work focuses on building reliable and scalable AI infrastructure, with particular interest in distributed training systems, reinforcement learning for robotics, and safety aware machine learning frameworks. I'm also actively involved in research on AI assurance, large scale learning systems, and emerging intelligent robotic collectives. Today, I'm presenting a work on JAX based differentiable framework for Bayesian cosmological inference, a system that brings automatic differentiation and GPU acceleration to the problem of estimating cosmological parameters. Let me open up with a framing question. How many of you have run a MCMC sampler and waited hours or days for it to converge on a 20-dimensional posterior? That waiting time is the problem this work directly attacks. The core insight is simple. If we can compute exact gradients of cosmological likelihoods, we can use gradient-based samplers that explore posterior orders of magnitude more efficiently than traditional random walk methods. Over the next 15 minutes, I'll walk you through the motivation, the framework design, Fisher forecasting, inference methods, and our DES Year 1 case study results. The challenge facing cosmologists today is that our inference pipelines haven't kept pace with the scale of our experiments. Traditional MCMC methods like Metropolis Hastings work well for small parameter spaces, but modern surveys like DES, LSST, and Euclid involve 20 or more parameters. Cosmological parameters plus nuance parameters for systematic effects like galaxy bias, intrinsic alignments, and photometric redshift errors. The fundamental bottleneck is gradients. To use advanced sampling algorithms like Hamiltonian Monte Carlo, you need gradients of the likelihood with respect to all parameters. Computing these via finite differences in 21 dimension requires 42 plus likelihood evaluations per step, and finite differences are numerically unstable. The results depend heavily on step size. The third problem is that existing tools like CAMB, Class, CosmoMC, and Cobaya are written in Fortran and C++. They are highly accurate, but they are not differentiable. You can't attach automatic differentiation to them. The opportunity we saw is that JAX, Google's numerical computation library, provides exactly what's needed: automatic differentiation, JET compilation for GPU acceleration and vectorization. The question was whether we could build production quality cosmological likelihoods in JAX. Let me describe what the framework actually is. At its core, it's a JAX library that implements the full 3x2 point likelihood pipeline for a DES-like analysis in a completely differentiable way. Every calculation, background evaluation, power spectra, angular power spectra, Gaussian likelihood is a pure JAX function that supports autodiff, JET compilation, and vectorization. The three main technical contributions are: first, the modular differentiable pipeline itself, validated against CCL at the 10 to power minus 3 level. Second, Fisher forecasting and survey optimization using exact gradient computation. And third, a hybrid inference approach combining SVI with neural transport that delivers accurate posteriors from very few samples. The key insight is that once you have a differentiable method, you can plug it into NumPyro and get NUTS sampling essentially for free. You also get Fisher matrices via a two-line Bayesian computation. You get gradient-based survey optimization. You get variational inference. All of this unlocks simultaneously once you have the differentiable forward model. The comparison point is Cobaya, the current state-of-the-art inference framework. Our NUTS sampler achieves 10x more effective samples per second on the same DES Year 1 analysis. Let me walk through the three main modules of the library. The background cosmology module solves the Friedman equation for a flat universe. This gives you the Kuhn moving distance, Hubble parameter, and a growth factor as a function of redshift. We use JAX-based Runge-Kutta integration for the ODEs, which make all the three quantities automatically differentiable with respect to omega c, omega b, h, omega naught, and omega a. The power spectrum module uses the Einstein-Hu analytic transfer function combined with HaloFit for nonlinear corrections. This is less accurate than a CAMB or a class, but it's fully differentiable placeholder. Our future plans include training neural emulators on CAMB outputs to get sub 0.1 accuracy while preserving differentiability. And in fact, we have surrogate models achieving less than 0.5%. The angular power spectra module computes C-cell for galaxy clustering and weak lensing using Limber approximation. All integrals use JAX-based quadrature. So derivatives with respect to redshift distribution parameters, bias parameters, and intrinsic alignment parameters are all available automatically. One technical challenge worth highlighting: integration with legacy Boltzmann codes. We handle this via three strategies: neural surrogate models, differentiable spline interpretation, or lookup tables using JAX custom derivative rules. and custom registration for wrapped legacy functions. Now let me describe the inference algorithms in detail. Hamiltonian Monte Carlo introduces an auxiliary momentum variable and simulates Hamiltonian dynamics to propose distant moves in parameter space. The key advantage in high dimension is that it avoids random walk behavior. Instead of proposing nearby points, it follows the geometry of the likelihood surface, leading to much lower sample autocorrelation. NUTS is an adaptive extension of HMC that automatically tunes trajectory length and step size. We implement it via NumPyro with our differentiable cosmological likelihood plugged in as a log posterior. The autodiff handles all gradient computation. For stochastic variation inference, we parameterize the posterior as a multivariate Gaussian and optimize its parameters by minimizing the KL divergence from the true posterior using the reparameterization trick. We enhance this via a block neural autoregressive flow to capture non-Gaussian posterior shapes. The neural transport hybrid is the most powerful approach for rapid analysis. A normalizing flow transforms the parameter space into Gaussianized coordinates, and we then run NUTs into the transformed space. With only 200 NUT samples after variation pre-training, we recover accurate posteriors in under 1 hour, compared to 20 hours for the full NUTs run or 40 hours for Cobaya. Fisher forecasting is one of the most common tasks in observational cosmology. You want to know before building an experiment how well it will constrain your parameters of interest. The standard approach is to compute the Fisher information matrix, the expected curvature of the log likelihood at the maximum. In practice, this means computing second derivatives of summary statistics with respect to parameters. Traditionally, this is done with finite differences, which requires 2n plus 1 likelihood evaluations for n parameters and is sensitive to the choice of step size. With our JAX library, Fisher matrix computation is trivial. We compute the Hessian of the log likelihood directly using autodiff. 2 lines of code, no step size to tune, and exact results at machine precision. More importantly, this opens up gradient-based survey optimization, the Dark Energy Task Force Figures of Merit, which summarizes the constraining power of experiments on dark energy, can be treated as a differentiable function of survey parameters like sky area, depth, and redshift distribution. We can then maximize it using gradient descent, automatically finding the optimal survey configuration. We also implement moped data compression, which reduces a potentially large data vector to a minimal sufficient statistic of the same size as the parameter vector. Because moped depends on model derivatives, a JAX makes it straightforward to implement, and the compressed likelihood preserves essentially all information. This table shows the raw numbers from our DES Year 1 3x2 point benchmark. The column shows Cobaya's Metropolis Hastings sampler versus our NUTS implementation versus an existing JAX NUTS baseline. The metric is effective samples per second, ESS per second, which accounts for both raw speed and sample autocorrelation. The headline number is 10.3x speedup from omega c, but look at the H parameter, 21x speedup. The reason is that HMC is particularly efficient for parameters that are well constrained and have clear gradient structure. The second part of the table shows precision results for Fisher computation and GPU scaling. The key point on Fisher is that finite differences produce step size dependent results, while autodiff gives exact consistent results regardless of parameter. For GPU scaling, we see near linear performance up to 4 GPUs, 3.7x throughput on 4 GPUs, corresponding to 92.5% parallel efficiency. For practitioners in the audience, the 20-hour wall time for 16,000 NUT samples may sound long, but these are nearly uncorrelated samples. Cobaya's 40-hour run produces 140,000 samples, but after thinning for autocorrelation, you end up with a far fewer samples that are effective. Our ESS per second comparisons account for this directly. Let me show you the key results. The 4 headline statistics at the top capture the more contributions. 10.3x ESS per second speedup for omega c. That's effectively efficiency gain over Cobaya. 20 hours on a single V100 GPU to generate 16,000 post-warm-up NUT samples. The equivalent Cobaya run took 40 CPU hours. Gradient computation cost 2.2 to 3x on a single forward evaluation. Orders of magnitude cheaper than finite differences in 21 dimensions. And with our SVI plus neural transport approach, we get accurate posteriors in under 1 hour. The bar chart shows ESS per seconds broken down by parameter. The gradient-based methods outperform Cobaya uniformly, with the largest gains for efficient parameters like H and omega b that have strong gradient information. The validation section on the right is critical. We are not claiming speed. We are showing that the posteriors are correct. The NUTS contours match Cobaya contours for all efficient and key parameters, validating that our differentiable likelihoods are numerically accurate at 10 to the power minus 3 levels against CCL. No framework is complete without an honest discussion of the limitation. So let me be direct about where this work falls short. The most significant limitation is the power spectrum module. We use the Einstein-Hu analytic approximation plus halofit, which is accurate to about 1% for the matter per power spectrum. For the current DES analysis, this is borderline. For LSST or Euclid, it's insufficient. We need differentiable neural simulators trained on CAMB or class outputs. We have initial simulators achieving 0.5% relative error on probability of k, but full integration in the pipeline is future work. The precision issue is subtle but important. JAX defaults to 32-bit floating point for GPU acceleration. For Fisher matrix elements, float32 introduces up to 2% bias for some parameter combinations. Our recommended approach is a hybrid precision strategy. Float32 for MCMC sampling, where stochasticity dominates. Float64 for Fisher forecasting and optimization. JAX's per operation precision control makes this practical. Memory is a real constraint. Covariance matrix operations scale as O of n in the number of data points. This limits up to 150 parameters on V100 hardware before memory becomes the bottleneck. Future scalable or future exascale analysis will need distributed covariance representations. On the future side, the three highest priority directions are differentiable emulators for production accuracy power spectra, extension to CMB, and spectroscopic probes, and multi-GPU operation for stage 4 survey analysis. Let me close by stepping back and summarizing what this work contributes and where it points. The technical results are strong. 10x or better sampling efficiency, robust Fisher forecasting without numerical instability, and a sub-R path to approximate posteriors via SVI and neural transport. These are meaningful improvements for production cosmological analysis, but the deeper contribution is conceptual. We have demonstrated that cosmological inference can be formulated as a fully differentiable program. This means that many or any gradient-based optimization on inference techniques from the machine learning world is immediately available to cosmologists, not as an approximation or a workaround, but as an exact validated method. This is timely. LSST is beginning operations. Euclid is collecting data. CMB S4 is being designed. These experiments will produce cosmological analysis with 50 to 100 parameters, and they'll need inference methods that scale. Differentiable programming provides that stability. My vision for this work is that differentiable cosmological inference becomes the standard paradigm for the next generation analysis, in the same way that AutoDiff transformed deep learning from a laborious manual process into something you can prototype in an afternoon. The cosmology community has the experiments. We are building the computational foundations to match. That's it from my side, and I'm happy to take any questions.